Now, there was a video associated with this one. This is what your slides would look like after you've watched the video. Hear me talk about things. Solubility guidelines is something that you learned about when you took Gen Chem 1, right? We might be talking about this a little bit, right? And then I go on and talk about a bunch of stuff that we're not going to discuss in class. Fusion and osmosis, all right? It's in the chapter, and actually, the chapter talks about osmotic pressure first before it talks about anything else. And really, we're not going to be that focused on osmotic pressure in this class. So we're going to talk about it a little bit, but that's why I put it for you here in the video. So you have to get it from there. And then probably near the end of the lectures for this chapter, we'll do one or two examples just to make sure you know what's going on with osmotic pressure. Okay, so I also like starting with vapor pressure because not a lot of people are really familiar with what vapor pressure is. It's hard to define it. So rather than asking you what you think it is, let me tell you what it is. And let's use an example here, okay? On my right, up here, we have a glass of water. I should have brought one in here, okay? Let's say I have this glass of water sitting here, all right, and it's just sitting there. And it's at this level, okay? You can't see it on your slide. And let's say we're at a nice, comfortable 25 degrees Celsius. And I walk away, and I come back in 2 hours. What do I expect to see, water level-wise? Will it be the same, or will it have changed? You think? It might. It might change. It might be. I don't know. 2 hours isn't really that long. Let's say I come back in a day. What's going to happen to that level of the water? Does it increase? Does it decrease, or does it stay the same? It decreases. Why is it decreasing? What's happening? Do we add any energy to it? Do we boil any of the water off? No. Why does it get lower? Here, let's say 2 days. In 2 days, it's down to here. Let's say in 5 days, it's down to here. Why is it decreasing? We're not doing it. It's always at 25 degrees. What's happening? Why? Why? What happens if I come back after 2 weeks? It's probably empty, right? What's going on? Come on, someone must have an idea. Yeah.
Evaporating.
It's evaporating. What does that mean? It's evaporating. You're right. It's evaporating. What is evaporation? Say louder.
Water to air, like to gas?
Water to gas. Liquid. We're going from the liquid phase to the gas phase. That's what evaporating is. It's not boiling. It's evaporating. And to really be specific, even though you just wrote this down, this is really vaporization. Because evaporating, I'm really going to be technical and split hairs. Evaporating is something related, but a little bit different. And let me tell you why. Look at this distribution over here. We've got the number of particles. Let's say that's water molecules. All right, and they all have some kinetic energy. So here's their average kinetic energy on the x-axis. Now the thermometer, that's measuring the temperature, that's your average kinetic energy. So let's say up here we've got our 25 degrees Celsius. That's the average. Now that's degrees Celsius. It's not kinetic energy, that's Kelvin, right? Kelvin is a direct relationship of the average kinetic energy. But just play along with me here, all right? There's a relationship. That's the average, but there's a distribution, all right? It's not a normal distribution, but that doesn't matter for this. It's a distribution. Somewhere out here, they've acquired enough kinetic energy to escape into the gas phase. Only these can go from the liquid to the gas because it takes energy, okay? Kinetic energy. But at 25 degrees, most of the molecules don't have enough kinetic energy to escape into the gas phase. Now, water is a volatile liquid, okay, but it's also got a lot of hydrogen bonding in there. So it's going to take some energy to get the water molecules to go from the liquid to the gas phase. All right, So that's what's happening here, all right? After 2 days or 5 days, it's these in the red area. These have enough kinetic energy to get into the gas phase, and then they fly away into the atmosphere and they're gone. Now, but they're replaced. This distribution is going to shift. You're always going to have a distribution of kinetic energies. So as molecules leave, right, the spread of the kinetic energy, it's going to fill out that same distribution, and you're always going to have some molecules out here at the tail end that have enough kinetic energy. Let's write this in. Enough kinetic energy to go from the liquid to the gas. That's why the volume keeps decreasing until there's nothing left. All right? This is vaporizing. Vaporizing is, strictly speaking, here, just to make things neat, okay? Vaporizing is doing this. Evaporation is very, very similar. Evaporation is when we do this, but we're doing it at a temperature that's below the boiling point. Because what's the boiling point of water? What's the normal boiling point of water? 100 degrees Celsius. We're at 25 degrees Celsius. Now, when it's boiling, all right, as we discussed with the phase diagrams, there you have an equilibrium between the liquid and the gas. But when you're boiling at that temperature, all of the molecules have enough kinetic energy to escape. And there's something else that's coming into play that we'll talk about in a little bit. But here we have the same transition, but we're at a temperature below the boiling point. That's the specific definition of evaporation, and that's the difference between saying something's evaporating versus it's simply vaporizing. Evaporation is just vaporization below the boiling point. But let's pretend, not pretend, let's put a cap on here. So when they do escape into the gas phase, they can't go off into the atmosphere. They stay trapped. All right? So now we have a slightly different situation. We still have the liquid escaping into the gas phase, and it had that kinetic energy, but now they're hanging out in the gas phase, and they're going to establish some equilibrium where some molecules that are in the gas phase can come back into the liquid phase. Now we can reach an equilibrium. Because the gas particles can't leave. When you have gas in a confined volume, what can we measure?
Pressure?
The pressure, okay? So if we measure the pressure going on in here, that's what the vapor pressure is. The vapor pressure is the pressure above the liquid. Above the liquid surface. Of a volatile substance. I really should say a liquid. So once it's reached an equilibrium, we can measure that. And I should actually add to your notes, it's not just an equilibrium. All of the equilibrium that we describe here, these are dynamic equilibria. And I'm mentioning that because equilibrium is something that we're going to be studying in much, much greater depth later on in this semester. By dynamic, that just means that we are constantly having liquid molecules escaping into the gas phase, and at the same time we have gas molecules that are condensing back into the liquid phase. So I walk away and come back in 2 days or 5 days or 2 weeks. As long as that's capped, the volume of liquid is staying the same. It's not evaporating. It's not vaporizing off and not coming back. So it looks static. It looks like it's not changing, but it's constantly changing. It's just changing in both directions. So we've established a dynamic equilibrium. It's dynamic because it's going both ways. I mean, because it's moving in both directions, but the net result is always the same. Okay, so that's a much detailed explanation of what vapor pressure is. That was a nice logical synthesis here, so let me highlight that for you, okay? Understand what vapor pressure is, because now we're going to start looking at it in even greater detail. Right? So there is a relationship between the vapor pressure and the temperature. And that's what's shown in this diagram from the textbook. Now, on the y-axis, we have vapor pressure, and the x-axis, we have temperature. Now, let's have a little talk about units here. Temperature, we're always working in degrees Celsius or Kelvin, okay? Mass, we're always working in grams or some metric version of that, right? But for pressure, there's about, 10 different units for pressure that people use. I don't know why, okay? I like to stick in atmospheres, but as you'll see, especially in this chapter, there's torr, there's millimeters of mercury, there's pounds per square inch. Let's hope we don't have to use the old English system, all right? Let's stay metric here, all right? I'm not going to quiz you on knowing what they are or converting between them, all right? But you have to know what they are because a lot of the examples use them, okay? Torr is the same as 1 millimeter of mercury, and there's 760 millimeters of mercury or torr. That's the same as 1 atmosphere. Okay? So in case you were confused by that, hopefully this will demystify it for you. All right, so what do we have going on here? There's a line, right? At 1 atmosphere here. So we were talking at the phase diagrams about the normal boiling points and normal things, right? Normal means we've got it at 1 atmosphere. So here we have 1 atmosphere, but you can look at the pressure scale and look at the temperature, and then we have four different materials here. This is diethyl. Doesn't matter what they're called, but I'll just tell you. This is diethyl ether. This is ethanol. This, of course, is water. And this is antifreeze. What's antifreeze again? Ethylene glycol, thank you. Okay, we've looked at these with respect to their intermolecular attractive forces, right? Which one has the strongest intermolecular attractive forces and why of those 4? There's a little review for you. Ethylene glycol. Why? What does ethylene glycol have that the others don't?
Hydrogen bonds.
They have hydrogen bonds, but water has hydrogen bonds. Ethanol has hydrogen bonds. So it does, you're right, this has hydrogen bonding. This also has hydrogen bonds. Right? We looked at all these. What else? It's bigger, so it has greater London dispersion forces. That's right, it's more polarizable. So this will give us stronger London forces. How many hydrogen bonds can water form with itself? 1, 2, 4, 8, 16? 2, right? Remember, water can donate 2 hydrogens and it can accept 2 hydrogens. So you can think of every molecule of water can be involved in 2 hydrogen bonds, both donating and accepting, okay? Ethylene glycol can do the same thing. It's got 2 places where it can both donate and accept a hydrogen bond. So it's got the same hydrogen bonding capacity as water does, but it's also larger, so we've got more London dispersion forces going on there. So things add up pretty quickly, okay? Ethanol can hydrogen bond, but there's only one donor and 1 acceptor. And then we have poryl diethyl ether over here on the left. What does it have besides London? Because everything has London. What else does it have? It has a dipole, that's right. So you have dipole-dipole interaction. Okay, now, take a look at how they are arranged here. At 1 atmosphere, all right, this is the temperature, okay? This is a graph of the vapor pressure. These are vapor pressure curves. So let's just look at water real quick. Water is in blue. So at a really, really low temperature, we have a low vapor pressure for water here. And as we increase the temperature, we can increase the vapor pressure of the water, okay? Just like I described what vapor pressure is on that previous slide, at say 25 degrees? Well, we can measure it at all these different temperatures. In fact, in lab next week, you're going to be doing an experiment just like this. You're going to look at the vapor pressure relative to temperature and do some stuff with that. All right, and it keeps going up. It's not linear, but it does increase. Okay, we have an increase here. It's not linear. But let's just focus on the increase for the moment. At some point, it's crossing 1 atmosphere. Right? We've got temperature and we have atmosphere. But this isn't. Don't be confused by atmosphere being the atmospheric pressure. This is the vapor pressure. Okay, that's what we're looking at here. At some point, this has a vapor pressure of 1 atmosphere. What's the temperature when the vapor pressure of water is at 1 atmosphere? What's that temperature? 100 degrees Celsius. What does that mean to you? What's 100 degrees Celsius for water? It's the normal boiling point. That's right. This is the normal boiling point of water. It has a vapor pressure of 1 atmosphere. Okay? So now we're getting to the actual definition of when something's boiling. Okay? This is the definition of boiling point. It's going to be when the vapor pressure is equal to the pressure above the liquid coming from the atmosphere. Okay? When the vapor pressure, so VP, is equal to the pressure above the liquid. Atmospheric pressure. In fact, it says it right here. This is what boiling point is. Definition. It's still transitioning from the liquid phase to the gas phase, so it's still vaporizing, okay? But specifically, the boiling point is whatever that temperature is where the vapor pressure of the liquid becomes equal to the atmospheric pressure above the liquid. It might sound a little confusing right now, right? But let it gestate for a little bit in your brain. Take a look at these other substances. They have similar curves, okay? Take a look at ethanol, all right, the green curve. We can still measure what the vapor pressure is of ethanol, okay? And it's also increasing, all right? When we get to now 1 atmosphere, that is going to be atmospheric pressure in this case. That's how we define what 1 atmosphere is. It's the pressure at sea level, okay, coming from the atmosphere. Well, so what temperature for ethanol, all right, it's down here. Now it actually tells us what it is, 78.4 degrees Celsius. So that's the normal boiling point for ethanol. It's that temperature that ethanol becomes boiling because its vapor pressure is now equal to the vapor pressure, or equal to the pressure above it. Okay.
Right. For ethanol, the normal boiling point is lower than that for water because ethanol has a higher vapor pressure than water does. All right, ethanol doesn't have as strong intermolecular forces as water does, so it has a higher vapor pressure. It's easier for those ethanol molecules to escape into the gas phase. It's more volatile. And so because of that, it doesn't take as much energy, the temperature doesn't need to be as high, for that vapor pressure to now become equal to the atmospheric pressure above it.
Ethylene glycol doesn't boil until you get way out here. Well, that's a terrible curve. Doesn't boil till you get way out here at a balmy 197 degrees Celsius. That's the boiling point, the normal boiling point for ethylene glycol. But it takes a lot more energy to get ethylene glycol to boil when you're at 1 atmosphere. All right, well, we already looked at that. There's much more intermolecular attractive forces on ethylene glycol, which means that the vapor pressure of ethylene glycol, is it higher or lower than it is for water? Who thinks it's higher? Who thinks the vapor pressure of ethylene glycol is higher? Who thinks it's lower? It is lower, right? It's lower because the vapor pressure, remember the definition of vapor pressure. That's just measuring the pressure of the gas that forms right above the volatile solution due to the molecules escaping into the gas phase. So if the vapor pressure is lower, that means you don't have as much coming out of the solution. So to get it to boil, boiling, right, you've got to get a lot more coming out of the solution. So the stronger the intermolecular forces are, the more energy you have to give that liquid to get it to go into the gas phase. So the vapor pressure is lower. The inherent vapor pressure is lower. It takes more energy to get it up here. All right, so it might seem counterintuitive to you. All right, this has a lower vapor pressure. Because it has the highest intermolecular forces. Which means that it takes more energy. It needs more energy to get the liquid to go into the gas. This might this might help. Let's start again with our 25 degrees distribution of water. Okay, so we started here where just this little bit was able to get from the liquid into the gas phase, right? This is where we started. And here's our beaker in the lower left at 25 degrees. Let's put a little Bunsen burner flame on here. And at 25 degrees, all right, we have a few fumes, right? We have a few molecules, these that are hatched in red, that can escape into the gas phase. And as I increase the temperature, so let's put more temperature on here. Let's get this up to, let's say, 75 degrees. As I increase the temperature, I should have switched my colors here. Red is hot, right? But at 75 degrees Celsius, we have more energy in the system. So what I'm effectively doing is more of this distribution now has enough kinetic energy to go from the liquid to the gas phase if I'm at 75 degrees Celsius. Does that seem straightforward? If I plot that out here on the left, now I've got temperature versus just energy. So we're just adding, we're making the flame hotter. So we're adding more energy to the system. This is stuff that we did in Gen Chem 1, right? There's a relationship between the energy that you add to the water and the temperature that water becomes. Okay? And that's what we're seeing here as I'm describing it. Until we get to temperature, until we get to 100 degrees Celsius. What happens once I get to 100 degrees Celsius here? As I add more and more energy to the system, is that curve going to continue to rise up? What happens to it? Say louder. Tell them.
Transition phase. It transitions from water to gas.
It transitions from water to gas. That's true. But what happens to the temperature of the water?
It stays the same.
It stays flat. Okay? When you get to the boiling point, this stays flat. Because here, on the rising part of this graph, you're increasing the kinetic energy of the water molecules. That's where that energy is going to, right? But once it's boiling, now that you know what boiling is, what we're doing is we're transitioning between the liquid phase and the gas phase. And so all the extra energy that you're adding to the water is going into this transition. Okay? There's a thermodynamic value that actually accounts for the energy it takes to go from the liquid to the gas phase. The delta H of vaporization. This is what's actually dictating, right, why that line is flat. Because all the energy that you're adding to the system, that's going into this transition. So you're not going to get it any hotter. So that's what's happening here at 100 degrees Celsius. When we're at 1 atmosphere, okay? Because the boiling point, this 100 degrees, this is dictated by the boiling point, which now you know the definition. The vapor pressure is equal to the pressure above the liquid. So what happens now when we climb a mountain? All right? Now I'm making these numbers up, but the overall idea is the same, all right? High up on a mountain, we're no longer at 1 atmosphere. Let's say we're now at 0.7 atmospheres. It doesn't take as much energy to get the vapor phase of water hasn't changed, okay? Whatever it is. But now the pressure above the liquid has lowered, so it doesn't take as much energy. At 90 degrees, let's say, now whatever the vapor pressure is of water, which hasn't changed, but now that's equal to the lower pressure at 0.7 atmosphere. So the water boils at a lower temperature. You all see why that is? If I were to plot this out, all right, this is at 1 atmosphere. If I were to plot this out at 0.7 atmosphere, the line goes flat at a lower temperature. Say it's 90 degrees, whatever. All right? We haven't changed the definition of boiling. What we've changed is the pressure above the liquid. And the vapor pressure hasn't changed. So that's why you may hear, like, you know, it takes, 3 minutes to cook a hard-boiled egg at sea level and 5 minutes at the top of a mountain. That's why. Because you can't get as much energy into that water. Once it's boiling, you can't get any more energy into it because any more energy you add is going into the transition into the gas phase. It's not going, you're not getting more energy to cook your egg. So it takes longer to cook things when you're higher up because the boiling point is now lowered. And that's because the atmospheric pressure, vapor pressure, it's all rolled up into one. All right, so the mathematical treatment of vapor pressure and working with volatile liquids and the vapor pressures that are produced from volatile liquids was all figured out by some French person named Raoult. I call him Raoult. My colleagues, some of them call him Raoult. I guess if you speak French, that's how you pronounce it. But I'm going to call it Raoult. And Raoult's law is a mathematical expression that lets us, figure out what's the vapor pressure when we have combinations of things, mixtures of volatile substances. And if we understand that, then we'll be able to understand what happens when we start putting non-volatile particles into these solutions. But let me start out by reminding you about something that maybe you learned about in Gen Chem 1. You had me for Gen Chem 1. We almost certainly did this. Dalton's law of partial pressure. Does anyone recognize what that is? It's really, really simple. Okay. Dalton's law, and let's just put it up here. Dalton's law of partial pressures simply tells us a way, or it's basically on kinetic molecular theory of how gases behave, how ideal gases behave, and their pressures, they're just additive. We take the total pressure just comes from the partial pressures of each individual gas that's in the mixture. So the example I like to use is if we look at the air pressure and what's in air, okay? What's the solvent of air?
Nitrogen.
Say it louder.
Nitrogen.
Nitrogen. No, just there's only one solvent, right? The rest are solutes, right? So the solvent is the component of the mixture in the greatest amount, all right, or greatest proportion. So that's going to be nitrogen. Nitrogen gas, so the partial pressure of nitrogen gas, plus the partial pressure of oxygen gas, and there's also some argon in there, and there's some other things as well, like carbon dioxide and carbon monoxide. But let's just talk about these three, because these three comprise the three major components of atmospheric gases. Nitrogen gas is about 78% the composition, so it's 0.78. Oxygen is about 21%, so 0.21. And argon is about 1%. And that pretty much adds up to 100%. So all of the other gases that you hear about represent far, far less than 1% of the gases in the atmosphere. But the point here is that they all add up, okay? And Raoult's law is no different. we're going to now add up the partial vapor pressures of every volatile liquid that's in a mixture. So it's not a gas mixture now. Now we have a liquid mixture. Liquid mixture, and these are all volatile liquids. And we all know what that means now. A volatile liquid is something that will produce molecules in the gas phase at some measurable amount at 25 degrees at normal conditions. That's how we classify a volatile liquid. Now you may also remember from Gen Chem 1 when we talked about isotopes and calculating what the molecular weight of atoms are and molecules and whatnot, and we were looking at the average, right? But it's a weighted average, remember that? And we looked at the fraction of each isotope in nature, and then we added it up, we made a weighted average. You all remember that? Yes? No? Okay. This is the same thing, right? This is going to be a weighted average. In this case, we're taking a weighted average of the partial, well, that's not the partial. Because it's weighted, that is partial. It's a weighted average of the vapor pressures. So this is the equation. It looks scary, but it really isn't. All the P1, P2, P3, those are the partial pressures coming from the liquids that are in mixture. Okay, so this is vapor pressure from material 1. This is vapor pressure from material 2. This is vapor pressure from material 3. And then the X is the proportion. It's the weight. All right, the weights are going to add up to 1. All right, but they're not always going to be equal weights. All right, that's why it's called a weighted average, not a normal average. A normal average is where you add 3 things up and you divide by 3. That's assuming that they have equal weight. A weighted average, you've got to factor in, right, the proportion that each one is in the total. They're not going to be equal. So that's what X1 and X2 and X3 are. These are the proportions. This is what we call the mole fractions. And you'll see what I mean by that as I take you through this first example. But it's simply just the fraction of each material, and we're always looking at molar relationships here. Okay, so they should all add up to 1, and we'll check that throughout as we're doing things. So that's what the equation is. Let's just practice with it. We are asked to find the total vapor pressure of a gas mixture consisting of, now we've got 16.2 grams of this material, which is butanol, and we're told what the vapor pressure of butanol is. And then I'll switch colors here, and we've got 127 grams of octane, and here's the vapor pressure of octane. So we have to do a few things here, right? But we want to plug things into this equation. So what do we got? We've got mass, and we have vapor pressure. So what's one of the first things you need to do to solve a problem like this? If we need the mole fraction and we're given grams, what do you need to do? Say it louder.
Convert it.
Convert what?
Moles.
Convert grams into moles. That's right. Hopefully an easy task for you all. But what do we need to convert? We want to go from grams of butanol, so C4H9OH. We want to get that, let's put the grams over here, okay? And we want to get that into moles, so we're going to do dimensional analysis. We're going to go from grams of butanol to moles of butanol. Right? What do we need to fill out this proportion? We need to know the molar mass. How do we figure that out? You got to go to the periodic table and get your calculator and figure it out. Okay, but this one's easy. Okay, and just for demonstration purposes, I gave you something that's just carbon, hydrogen, and oxygen. So let's just do a quick back of the envelope calculation. You should be good at doing this by now. Okay, carbon is about what? 12, right? And we've got 4 of them. So 4 times 12 is what? 24, 48, right? And you've got how many hydrogens? 10 hydrogens. And each hydrogen is about 1 AMU. I know it's 1.00079, but you know this is okay for this demonstration. All right, so that gives us 10, and then we have 1 oxygen, and we'll go with 16 there, so that gives us, what is that, 14, 74. Okay, good enough for now. 74 grams per 1 mole. Make sure you put the number by the right unit. Make sure that it's set up so that your units cancel out. That way you never have to remember again, for all of you who haven't had me before. All right? I know some students memorize, oh, if I go from grams to moles, I have to divide by the molar mass. Or I multiply, I forget, whatever. And if I'm going from moles to grams, I have to do the. Don't try to memorize that. Just use dimensional analysis and set it up so that your units cancel out, and you'll never get it wrong. Okay? Really easy. All right, so how many grams? We've got 16. I knew I had grams in front of that for a reason. I'm getting ahead of myself here. We were given 16.2 grams of butanol. There. So now we need to calculate how many moles we have. So that's 16.2 divided by 74, and that gives us 0.219 moles of butanol. Is that what you all got? Good. You always got to double check me. Just keep me on my toes. All right, so great. So now we know the moles of butanol. Now we need to get moles of octane. So let's do the same thing. We've got 127 grams of octane, which is Ch10. What's the molar mass of octane? Doing the same back of the envelope calculation. 114. Is that what you got? Anyone else? Yes? No?
Mm-hmm.
That's what 114. That sounds right. I'm just glancing at my notes. Yep, 114. So 114 grams per mole. So how many moles do we have?
1.11.
1.11 moles of C8H18. So now we need to get the mole fraction. We know how many moles of each material we have. Okay? How do we get the mole fraction? We need to find out what the total is, and then what's the fraction of that total coming from this and the fraction coming from that. So we need to total these up. That's going to be, looks like about 1.33 moles total. So now we can get the mole fraction. So the mole fraction for butanol is going to be 0.219 divided by 1.33. And the fraction for octane is going to be 1.11 divided by 1.33. And I don't want this in percent. We want to keep this as a fraction. So 0.219 divided by 1.33. Here I have 0.165, and 1.11 divided by 1.33 gives me 0.835. And these two better add up to 1, because this is the mole fraction. And we only have 2 components here. And just by looking at it eyeball, yeah, these should add up to 1. So that's your check. So check plus. Okay, now we have all the information we need to calculate what the total vapor pressure is. Because now we can plug this all into Raoult's law. So P total is going to be equal to the mole fraction of butanol, right? That's 0.165, multiplied by the vapor pressure of the butanol. That was given to us as 5 torr. And we're going to add to it, just like we do for weighted averages, okay? Now we're going to add the weight of the octane. That weight is a mole fraction of 0.835. We multiply that by its vapor pressure, which is 10 torr. And that will give you what the total vapor pressure is. And I got 9.18 torr. Now, if you just step back and think about it, one of them is 5 torr and one of them is 10 torr. So you should already be thinking, what range should this answer be? If it was 100% butanol, here's the vapor pressure, right? That vapor pressure is vapor pressure. It doesn't matter how much there is. If it's pure butanol, the vapor pressure is 5. If it's pure octane, the vapor pressure is 10. And if we're mixing them in some proportion, the final should be somewhere between 5 and 10. It's not going to be 7.5 though. The only way it's 7.5 is if everything is equal in a normal average, but that's not what this is. This is a weighted average. See where I'm getting this from? Okay. So it looks complicated, but it's really nothing more than calculating a weighted average. Let's practice a little bit. This is the first chance for you guys to work as a community. We don't need to worry about the bottom part of this one. Let's just do the top part. All right? Same exercise. Work it out. Discuss with the neighbors on your island if you're having trouble with it, or if you're not having trouble, compare with the way that they're doing it. See if you guys get the right answer. If you're confused, ask each other for help. You can ask me for help.
Yeah. So, he did, he found each of them.
All right. The end part of this was great because I heard over here, well, do you always divide by this number or whatever? And then jumped in and explained, no. You do it this way for each one. It's going to be different, and this is what you do. That exemplifies what I would hope would happen with everybody here is that if you make a little mistake or you don't understand something, I'm always here to help you, okay? But if someone else at your station can show you how they did it and how to do it correctly and how to correct your mistake, then you're helping each other. And that's something that I really, really want to foster in this class because hopefully you're going to maybe start working together outside of class as well. Or you'll be seeing each other in the lab as well, okay? So that's kind of what I mean by a community of learning. So that was great. You didn't know I was watching, but I was. All right, I don't want to leave anyone in the dust, so I'm just going to blow through this one. I'm going to do it rather quickly, okay? But that's because I think most of you have this answer correct. But I want the correct solution to be up here. So let me just go through it. It's the same mechanics as what we did before, okay? We're starting with grams, so we need to go from grams to moles. So let's just work with, we'll start with heptane. We're given 13 grams of heptane, C7H16. That has a molar mass of, what'd you get? I don't want to count it up.
100.
100 grams per mole. So that's easy. I don't need a calculator for this one. 0.13 moles of C7H16. And then we're given 87. This is of octane, again, C8H18. That had, what did we say, 114? 114 grams per mole. So how many moles is that?
0.76.
0.76 moles of C8H18. We add these up, we get 0.89 total. So our mole fractions then is going to be 0.13 divided by 0.89 and 0.76 divided by 0.89. And that gives me a mole fraction of 0.146 and 0.854. Feel good there? Let me just write. These are the mole fractions. These should add up to 1. And let's just check. It does. All right. Or very, very, very close. Now we multiply these by their vapor pressure. So the, what is this? Heptane has a vapor pressure of 31 torr. And the octane has a pressure of 11 torr now. So it was 10 before. Now it's 11. Maybe we'll talk about why there's a difference, but it's 10 versus 11. Maybe it's rounding. We don't need to talk about it. I don't want to get off course. We can talk about it if you want. All right, so this then gives us, where am I? We multiply that together, we get 4.53, and this gives us 9.39, and that adds up to about 14, right? Which, I mean, you can be another decimal in there. I just wanted to show the solution of how I got to the answer that almost all of you were able to get as well. And if you didn't get it, hopefully now you can see where the mistake was. Any questions on the mechanics? Yeah.
So for how does vapor pressure exist?
How does vapor pressure exist when things are not covered? So when, yes, the way we define vapor pressure, you have to measure it, right? It's at the surface. Right? It's the pressure of the gas that evolved from the liquid measured at the surface of the liquid. So the only way to actually measure it is to have it capped.
How do things boil if they're not covered?
How do things boil if they're not covered? So going back to our definition last Wednesday or last lecture, right? Boiling, right? They'll still boil because it's not capped, but now you've got atmospheric pressure on top of it, or whatever the atmospheric pressure is. If you're at sea level, it's 1 atmosphere. If you're at the top of a mountain, it's like 0.8 atmospheres, whatever. Remember that the boiling point, that's a temperature. It's not a vapor pressure. The boiling point is a temperature where the vapor pressure coming from the liquid is now equal to whatever the atmospheric pressure is pushing down on it. Okay? So if we have this mixture, okay, this has a total vapor pressure of 14 torr. Now, if I'm talking in atmospheres, I don't want to do the conversion. The point is that at some temperature, we can get this mixture to boil. And that temperature will be such that the temperature that gets the vapor pressure high enough to match whatever the atmospheric pressure is underneath. Because remember, there's this curve. We're going to talk about this curve again in a minute. There's this curve. The vapor pressure is unique to a given temperature. But as you change the temperature, you're changing the vapor pressure. This is vapor pressure. This is temperature. Okay, so, something else to think about. Oh, in fact, I mentioned, why is it 10 torr versus 11 torr in the previous one? But, this says it's at 25 degrees. We weren't told what the temperature was at the earlier problem, where the vapor pressure for octane was 10. So it could just be that maybe it was at 20 degrees. And so at 20 degrees, the vapor pressure of octane is 10 torr, and at 25 degrees, it's gone up a little bit to 11 torr, right? That's fine. How about take a look at, let's see, heptane. Heptane has a vapor pressure of 31 torr versus butanol up here. Here, let's put these both. Butanol had a vapor pressure of only 5 torr. And that's a pretty big difference. Why is the vapor pressure of heptane so much higher than the vapor pressure of butanol? Say louder, sorry.
Hydrogen bonding.
Hydrogen bonding, okay, yes. So butanol can hydrogen bond. Heptane cannot hydrogen bond. So we would expect higher intermolecular forces or stronger intermolecular forces for butanol, meaning that it's going to be much more difficult for butanol to naturally escape into the gas phase. So you'd expect a lower vapor pressure for butanol. Yeah. Anyone else? That's a good enough reason for me. All right? So keep thinking about intermolecular attractive forces, all right? Because butanol has higher intermolecular attractive forces, it makes it more difficult for it to, on its own, just naturally escape into the gas phase. So side by side, apples to apples, at the same temperature, okay, the one with the stronger intermolecular attractive forces will have the lower vapor pressure because it takes more energy to get those molecules to escape into the gas phase. Okay, so now let's bring this around to colligative properties. Now we understand what vapor pressure is, we understand what it is in mixtures, we understand how to plug and chug in Raoult's law equation. So before we do that mathematically, let me remind you what colligative properties of solutions are. Okay? It's the effect that the non-volatile solute particles has on a volatile solvent. Okay? And as you'll be seeing in the next couple of lectures, here let's stay in red, it's the number of particles that matter. It doesn't matter what those particles are as long as they're non-volatile. It could be sodium ions. It could be glucose molecules. It could be pebbles. Okay? It doesn't matter as long as it's non-volatile. And the definition of non-volatile is it does not escape into the gas phase under standard conditions. Now, we've been talking about vapor pressure, right? Colligative properties has an effect on vapor pressure. And as you're about to see, as you add non-volatile particles to volatile liquids, it lowers the vapor pressure. We're going to look at what that effect is on the boiling point. It raises the boiling point. The freezing point, as we already discussed, it lowers the freezing point. And osmotic pressure, when we get around to talking about osmotic pressure, it increases the osmotic pressure. Okay? Now let's go back and look at how it lowers the vapor pressure. And so we're going to use Raoult's law now, and we're going to do a different calculation now. Now we're going to look at vapor pressure of an aqueous solution of sucrose. Now sucrose, right, that's a sugar, okay? I'm not going to draw out the formula for you, okay? It's two molecules of, it's a molecule of glucose and a molecule of fructose. Doesn't matter. Here's the molar mass, okay, so we can get it into moles. What's important to know about sucrose is that when you put it in water, it stays as sucrose, all right? It's not going to turn into multiple particles. Think of this as a non-volatile substance. Think of this as a non-volatile particle.
It doesn't ionize.
It doesn't ionize, okay? It has no vapor pressure. It's well, yeah, in this case it doesn't ionize, but for now, just know that it does not go into the gas phase. It's a non-volatile particle. And now let's do the same calculation, okay? Let's see what do we got here. It's a 66% mass-to-mass aqueous solution of sucrose. So we got to get this, okay, so it's another curveball that the textbook is throwing at us. It never does anything straightforward. So you're told that this solution is basically 66% sucrose in H2O. And it's mass to mass. So I wouldn't do this to you on an exam, okay? But you should know, and you knew how to do this back in Gen Chem 1. You're given the percent in the solution, and percents out of 100. So if we want to know what's the mass, because this is mass to mass percent, we just take it out of 100 grams. Remember, when you have percent composition from Gen Chem 1, it doesn't matter how much material you have, the percentage of each component is always the same, right? So if I know that it's 66% sucrose, then if I have 100 grams of the material, 66 grams must be coming from sucrose, and the rest must be coming from the water. That's just a way to decode this word problem with these. Let's get this into moles. So we're given the molar mass of sucrose. It's 342.30 grams per mole. Water, we know, 18.015 grams per mole. Now let's figure out how many moles we have here. 0.193 moles of sucrose, 1.887 moles of H2O. Add these up. About 2.08 moles total. Is that what everyone's getting? So now let's get our mole fractions. How do I know I did it right? Because my mole fractions add up to 1. Check plus. These are the mole fractions. All right, so let's apply this now to Raoult's law. Let's calculate the total vapor pressure coming from this. It's the mole fraction of the sucrose, 0.09, multiplied by the vapor pressure of the sucrose. What's the vapor pressure of sucrose? Sucrose is non-volatile. So what's the vapor pressure of a non-volatile substance? It's 0. There is no vapor pressure, but it's there. It's in the solution. So we're applying it correctly to Raoult's law. All right. So now let's calculate the vapor pressure component coming from the water. The mole fraction from water is 0.91 multiplied by the vapor pressure of the water. Now this is another textbook trick. What's the vapor pressure of the water in this problem?
Is it 760?
760. Who said that? Why is it 760?
It's at 100 degrees Celsius.
Because it's at 100 degrees. That's exactly right. In the problem, it's at 100 degrees Celsius. Again, I wouldn't trick you on this on an exam. I would just tell you. All right? But at 100 degrees Celsius, as we've been talking about, right, that's the normal boiling point of water. So if you're told that this is at 100 degrees Celsius, okay, then we know what the vapor pressure of water is. Yeah, it says calculate the normal vapor pressure. So anytime you see normal, all right, that means you're at 1 atmospheric pressure, okay? So the vapor pressure here is 760 torr, but we want our answer in atmospheres. So let's go ahead and put the answer in atmospheres, okay? The vapor pressure is 1 atmosphere. Let's just remind ourselves what this is. This is the mole fraction, and this is the vapor pressure. This is the mole fraction, this is the vapor pressure. So what do we got? What's the total pressure going to be? 0.91 atmospheres. Because this term goes to 0. So without the sucrose, if it was just pure water, at 100 degrees Celsius, we know that the vapor pressure is 1.0, right? Let's just write that in. Vapor pressure of pure H2O is equal to 1 atmosphere. Okay? So we just plug that in. But by making a solution, an aqueous solution, we are effectively lowering the vapor pressure. Now this was a mathematical explanation of why the vapor pressure is lowered. Let's now step back from the math, okay, and just think about pretty pictures again. And let me just give you a different way to think about the same concept, going back to the same chat that we had on Wednesday about what vapor pressure is to begin with, okay? Here's our pure water, 100 degrees. So here, we'll put some flame under our Bunsen burner. We're heating this up. You can see the bubbles coming up in the water. All right, we are at the boiling point. We're boiling here. We've got 1 atmosphere of pressure coming down from the atmosphere because we're at sea level, okay? So this is the normal boiling point of H2O. This is, just to remind you, this is where the vapor pressure is equal to the atmospheric pressure, which in this case happens to be 1. Now we're going to take that same beaker and I'm going to put some non-volatile particles in here. Let's just make them in red. These are non-volatile particle. It could be sucrose, or maybe we put some table salt in there. Maybe we're going to make some pasta. So we dump a bunch of salt in the water and that dissociates into sodium ions and chloride ions. Those are also non-volatile particles. Okay, we'll be getting to those in a little bit. Doesn't matter what they are though, right? Because colligative properties is independent of the material that's causing this. It's just how many particles there are that are non-soluble. That's what ultimately matters. So what's happening now? We've got some water molecule in blue wants to get out, right? It has enough kinetic energy because we're cooking it at 100 degrees. Normally, if there wasn't anything to get in its way, this little water molecule will be able to escape to the gas phase once it gets to the surface. No problem. Right? That's what's happening here, right? It was down here, it goes up here, and then it goes off into the gas phase. But now we've got these red things that aren't going into the gas phase. It's getting in the way. It makes it harder. It's a barrier for these molecules to escape into the gas phase. Just think of it that way. Right? These are a barrier for the water molecules, liquid, to escape into the gas phase, all throughout the material. So what do we need to do to get that to boil again? We need to get that vapor pressure back up higher so that now effectively it will match whatever's coming down from above it. So we need to get this even hotter. We need to get this up to 102 degrees Celsius. And in doing so, we're giving the whole system more kinetic energy so that these little blue water molecules can get past the barrier. We want to overcome that. Overcome with higher temperature. So if I were to plot this out, this is similar to, or it's the opposite of when we were cooking that hard-boiled egg on the top of a mountain. Now we're trying to cook the hard-boiled egg by putting non-volatile particles in there, okay? We can actually get more energy into that water before it boils. Because if I look at the normal boiling point, 100 degrees Celsius, remember what happens, right? It goes flat. When it's pure water, we can only get that much energy into the water at the boiling point. Because if we added any more energy, it's just going to the phase transition. It's not making the water any hotter. So the water can only hold on to so much energy. Because remember, that's where the delta H of vaporization comes into play. That tells you how much energy is related to the conversion of the liquid phase into the gas phase. But if we put these non-volatile particles in there, we now need to get this more energy, more energetic, so we need to increase the temperature, and now we can get it to boil again. So effectively what we're doing, here I should have put this down below. Because now what we can effectively do is increase the boiling point, here, let's say 102 degrees Celsius. This is with non-volatile particles. So you get more energy. Things will cook faster. You might think that's why people put salt in the water when they're making pasta, so that their pasta will cook faster. But really, the amount of salt that you put in isn't enough to get it to raise that much. It's mostly for taste. But the idea is there. And we'll actually be doing some calculations. How much salt do you have to add to this water to get it to rise by 1 degree Celsius? We'll actually be doing that calculation. All right? We can do other calculations where we can figure out how the freezing point is going to be lowered by adding particles. Okay? But thinking of this as just a barrier, a physical barrier, is another way to just empirically think about this stuff. But mathematically, you can still prove that in the same way. You can use the same barrier idea to think about why the freezing point goes down. We'll just end with that, okay? On a really, really cold day, like we had last week, okay, where we're at the freezing point, okay? And remember, the freezing point is the same as the melting point. It just depends on which direction you're going, okay? But when we're at 0 degrees, the normal freezing point, 0 degrees Celsius for water, okay, we have an equilibrium set up again, where we have H2O molecules in the liquid phase are going into the solid phase, and we have molecules in the solid phase going back into the liquid phase. If we start adding salt to the road, okay, salt, this is going to be a physical barrier to the H2O liquid molecules packing into a solid, right? It's got to pack in there. Now it doesn't create a barrier for the solid to melt back in to liquid. So this goes just fine. So solid goes back into liquid the way it normally does. So when we have salt on the road, all right, going from the solid to the liquid is still the same, but now the liquid doesn't go into the solid quite so easily because it's got to overcome this barrier. It's got to get around all of these non-volatile particles to finally get into the crystalline structure that it needs to be in to form the solid. So to get that liquid into a solid, you've got to get things that much colder so that you can drive this back to an equilibrium and get the liquid back into the solid, because you've constantly got solid going back to the liquid. So we need to get things even colder to now get it to freeze. Just thinking about it using the barrier analogy.